Welcome to Waitman Science. Today's topic is Lewis dot diagrams. Lewis dot diagram is a depiction of the valence electrons that you find around an atom. They end up looking like this. Valence electrons are those electrons that are found in the outermost shell or orbital of an atom, and this is where the chemistry occurs. These are the electrons that are gained or lost or shared between atoms. In a Bohr-Rutherford diagram, we see the multiple shells or orbitals of that particular atom, but the ones that we're really concerned about are those outermost. Here's magnesium. As you can see, it's got two completely full orbitals, and then its final orbital only has 2 electrons. In this case, it has space for 6 more. If we were to look at any Bohr-Rutherford diagram, we see that the orbitals correspond with the periods of the periodic table. And if we were to draw the first 20, they'd look something like this. We'd notice that the top row has a single orbital, the second period has 2 orbitals, 3 periods, 3 orbitals, 4 periods, 4 orbitals. In the first group, we see that each has 1 valence electron. The second each has 2, third 3, and so on. In that final group or column, the 8 or 18 column, we'll notice a bit of a pattern change. We've got 2 in that first, the helium, but that's a completely full orbital. In the second period, we have 8 valence electrons, as is the case in the third. Those are both full as well. There's only 8 in that orbital. If we were to continue on, we'd then see there was 18. For Bohr-Rutherford and Lewis dot diagrams, we really limit ourselves to the first 20. But a Lewis dot diagram is very particular in how it's drawn. We have the same symbol of the element that we'd get from the periodic table, but then we represent the valence electrons with dots. And the filling order is kind of important of this. If we were to put 1, we'd be specific to put it at the top. And this is much like the Bohr-Rutherford diagrams, where we're trying to show that the electrons are as far away from one another as possible. Sure, we could just draw them randomly around the edge, but when we follow this pattern, we tend to make it quicker and easier to identify the valence electrons and the number and make certain predictions about how it will bond. So we go top, bottom, left, right, top, bottom, left, right, until we have our complete 8 valence electrons, as we saw with the noble gases. If we were to look at each group, we'd end up with a representation like this. We notice here that our Bohr-Rutherford diagrams have increasing number of orbitals, but in each case, in group 1, that outer orbital or valence shell only has 1 valence electron, and we can see that depicted in the Lewis dot diagram. Much quicker, much easier to draw than the Bohr-Rutherford, but still gives us that important piece of information about electrons that are being reactive. Group 2 each have 2, group 3, and so on. Until we get to the noble gases or the inert gases. Inert because they're not reactive. They neither need to gain nor lose electrons to have that complete outer valence shell. You can see here they all have the 8.